Okay, good morning, students. I hope you are fine. So, for today, we will apply Gauss. We will study Gauss. So, as we have seen previously in the previous chapters, then we can deduce the electric field. That we can deduce the electric field for a point charge. It can go radially outward for a positive charge, and it goes inward for the negative charge. We have seen also that for a continuous charge, we must define an element of charge dq and identify the point where we want to deduce the total electric field, and then the total electric field, and then we deduce dE. After we deduce dE, we integrate to get E. So you remember the formula of dE is 1 over 4 pi epsilon 0 dq over r square ur. Then when we identify dE, we integrate to get the total electric field. But you remark that sometimes the geometry of integration is a little bit difficult, and the integral is sometimes difficult to find. So a very Chinese mathematician scientist called Gauss, proposed to use symmetry to find the electric field E without passing by dE and the integration. So this is the purpose of this chapter. Now I will explain to you the codes. You have the PDF. You have the PDF document. So let us explain. As we said, Gauss proposed to consider an imaginarily closed surface that encloses the charge distribution. Before using the Gauss law, we must define what is the flux. The flux is a value, an algebraic value deduced from a certain vector, which will diffuse according to a surface. So the flux is a general definition, but in our case, for physics, for electricity, we use the flux of the electric field. Now let us first define what is the flux in general. In general, the flux, if we have an air stream with velocity v, and if we have an air stream with velocity v, and we have an angle between v and the area surface, A, we can deduce, we can know which one is can be accepted. So if we have V, then we remark that according to the figure here, we can remark that it's according to the angle between A and V, we have a certain intensity of the flux. If the airflow is parallel to V, we can consider that the total air is passing through the loop. But if it has a certain angle theta, if V has a certain angle theta with A, in this case, we don't have the totality of the flux, so just a part of it will pass. You remark here. So for the flux of an electric field, we take a random surface, and we take a small surfaces dl as element. The electric field, the idea of symmetry due to Gauss law, consider if you divide your closed surface into small parts. In these small parts, we can consider without error that the electric field is constant. So here, because the electric field is constant, in the integral, we can exit it from the integral. So we have many possibilities, and we remark that to get the flux, you must just calculate the dot product between E and A. So because the squares have been taken to be arbitrary, no picture. I will see just a minute. I will check, I will add the picture just. And now you have the picture. That is, so let us continue. So you remark here that the flux of the electric field is just the dot product between E and dA. So the Gauss law will consider that the electric field at the small area dA is constant. So to find the total flux of your surface, you have to sum E delta A. And if we have a continuous surface, it means that this sum will be the integral. That is, so electric flux through a Gaussian surface. What is Gauss law? So Gauss law relates the flux of an electric field through a closed surface, which is a Gaussian surface, to the net charge Q enclosed, that is inside or enclosed in that surface. So in this case, you will have epsilon 0, the integral of E dA is Q enclosed. That is the formula. What does it mean? It means that if we want to deduce the electric field, we have just to find the enclosed charge inside your closed surface. You remark here that the integral must be operated over the closed surface. So we have seen previously Coulomb's law. So we must have the correlation between Gauss law and Coulomb's law. So applying using Gauss law, if we have a point charge Q with positive charge plus, we take a closed surface, a circle around the charge, and then we will apply Gauss law. So epsilon 0, the integral over the closed surface E dA, will be epsilon 0, the integral. You remark that dA also is vertical radially, like this. So it is parallel to E. This is why we can remove the vectors and we get E dA directly. And according to Gauss law, the electric field is constant in the small area dA. So we can exit it from the integral. This is why it will be simple to integrate. So look here, if we integrate, we will have EA, epsilon 0 EA Q enclosed, and A is 4 pi r squared. So we will deduce the same formula that from Coulomb's law. Now, the most important idea in Gauss law, that an isolated conductor will not have charge inside it. Just remember this So it is important, if you have a conductor that is isolated, there is no charge inside it all the time. So we will apply this law for a conductive plate. In this case, if you have a positive plate charged, but it is conducting, and if we take a closed cylinder as Gaussian surface, as we said at the beginning, that the Gaussian surface will be closed. So will be closed. In this case, if the Gaussian surface is closed, we will consider just the charges which are inside it. So if we represent here, you remark that there is no charge E equal to 0 inside the plate, and outside you have the electric field. You have the electric field going outside in this direction, and it is parallel to L. So in this case, this is a perspective view if you have a conducting plate. So in the left side, E equal to 0, and on the right side, you have E parallel to L. So let us now deduce the total flux and deduce the electric field. So let us take cylinder as in the figure. There is no flux through the internal cap because the electric field inside the conductor is 0, and no flux. Look here in the figure. So on this cap, the electric field is 0 because we are inside the conductor and there is no charge. And in the lateral side, there is no flux because the electric field is perpendicular to A. So the dot product will be 0. So what is remaining? Just the external cap. Okay? So just the external cap, and we replace, so phi is EL equals to Q enclosed over epsilon 0. The charge in the plate is sigma A, so we replace sigma A epsilon 0, EA. We can cancel A on both sides, and we get E is sigma over epsilon 0. Now, let us apply Gauss law if you have a cylindrical symmetry. Generally, we follow the symmetry of the problem. It means if you have a cylinder, you will take a cylinder as Gaussian surface. If you have a sphere, you will take a sphere as Gaussian surface. It depends on the symmetry of the problem. So in this case, we will take a wire which is cylindrical, positively charged with linear distribution lambda here. So we apply Gauss law. We take a cylinder as I explained to follow the symmetry of the problem, and then we have the total. Where is the electric field in our case? Look to the electric field. It goes according to the lateral surface. So with on the tops, there is no electric field because it is perpendicular to A. So only the lateral surface will be concerned. And what is the total surface is 2 pi r, the circumference, times h. So here, if we apply Gauss law, the flux phi if we apply Gauss law, the flux phi will be like this. phi is EA cosine theta, so it is EA. What is it? Because E and A are parallel, so E 2 pi RH cosine 0. It is E 2 pi RH. In this case, phi is 0 through the end caps because E is radial and vertical to A. So here, let us continue. So the total enclosed charge, phi is 2 pi RH, it's Q enclosed over epsilon 0. In our distribution, because we have linear distribution, it will be lambda H over epsilon 0. So E is lambda over 2 pi epsilon 0 R. It's the line of charge. Now let us apply Gauss law using planar symmetry non-conducting sheet. So if it is a non-conducting sheet, you remark here that we have electric field on both caps. So in our representation, we have electric field in this side and also inside, because it is an insulating material. Then let us apply Gauss law. So we must integrate over the whole surface, which is the cylinder here. We have the two caps and the lateral surface. Then if we calculate phi, it is the integral of EDA. It's Q enclosed over epsilon 0. So it is EA plus EA for the two caps here. So we have E times A because they are parallel, but there is nothing on the lateral surface. You can ask if we have here a plate, just ask your questions if you didn't understand something, okay? So, so here, if we take a plate which is insulating, there is electric field everywhere, outside the plate and inside the plate. So here, you remark that if we integrate, we will have just the flux due to the lateral, caps, to the two caps, but also the lateral, it will disappear. Why? Because the electric field is horizontal and the area surface is vertical. Okay, so we will get that EA let us there is a question from a student asking about the cylindrical symmetry. As I said, let us return back to the cylindrical symmetry. As I said, if we have a plate if we have a plate, we must take a closed surface, and the closed surface will be a cylinder. Then when you take your closed surface, you will consider just the charge which is inside. Here, the electric field is going outside, so we have the electric field in this direction horizontal. But the area surface, here they are parallel, here they are parallel, but here the electric field is perpendicular to the area surface. So there is no flux for the lateral surface, only the two caps will remain. So I will have EA plus EA, so twice EA is equal to sigma A. Okay, so twice EA is equal to sigma A. We have E is sigma over 2 epsilon 0. This is the formula for non-conducting sheet. Let us return back. We take, yes, for your question, Miss Tizeri, why we take a cylinder as a Gaussian surface for sheets. We take a cylinder for Gaussian surface for sheets because we must take a closed surface. If you take something plain, it doesn't run. And the why it is a cylinder? Because cylinder, you have vertical side, you have lateral side. If you take a sphere, for example, there is no symmetry. It will be difficult to have the electric field parallel or perpendicular to A. But if you take the cylinder, you remark that sometimes A is parallel to A, and sometimes E is parallel to A, and sometimes E is perpendicular to A. So it's better to work with this symmetry, which is a cylinder. Okay, miss? So for this case, for when you have a sheet, because the sheet is infinite and you cannot close it, you must take a closed surface, a cylinder. And why the cylinder? Because sometimes it is perpendicular and sometimes it is zero. So you have the symmetry. Okay, miss? Now, for example, what we have seen, so you remark that the fact that the material is conducting or no is important. Let us see quickly the cylindrical symmetry. Here, if you have a wire, you must take, which has a cylindrical symmetry, you must take a cylindrical symmetry also as a Gaussian surface. So your Gaussian surface must be automatically a cylinder. This is why. Okay, so, and then you study if it is parallel or perpendicular to A to get which surfaces are contributing to the flux. Now let us continue. Just ask your questions. If you have questions, I'm going to read them and explain them. Okay, now let us see the case if you have two conducting plates. If I have a conducting plate with a surface charge sigma 1, positively charged, so here, and the second sheet is also positively charged with sigma 1. You know that if you have a positive charge, the electric field is going outside, and if you have a negative charge, it goes inside. So if because it goes outside, so the electric field is in this direction. Okay, the electric field is in this direction, and the charge will go, if this is the first charge, positively charged, the first plate, it goes outside. This is a negatively charged conducting plate, it goes inside. Now if you gather the two plates, so there is attraction between the positive and negative charge. So the positive charge which was in this side will go to the other side. So instead of having sigma 1, it will be 2 sigma 1. They will, all of them, migrate to the internal side. Also for the negative charge will migrate to the internal side. So you will have 2 sigma 1. And there is an electric field only between the positive and the negative charge. Okay, so Uh, and what is this principle? We have seen that it's the work of a capacitor. The capacitor, you have charge between the two conducting plates. You have electric field between the two conducting plates and no electric field outside. Okay? So, since the plates are conductors, then we bring the arrangement of C. The excess of charge will move to the internal plates and we get, so if we apply Gauss law, you take a cylinder, you will have EA. So if I apply Gauss law here, I will take a cylinder in this area, it is EA and the internal charge is 2 sigma 1. So I will replace, I will have EA is 2 sigma 1 over epsilon 0 A, it's sigma over epsilon 0 A, and we will have E is 2 sigma 1 over epsilon 0 with sigma is twice sigma 1. So from the positively charged plate to the negatively charged plate and E equal to 0 outside. Now if we apply Gauss law for a spherical symmetry, if you have a sphere of charge like here, we have spherical conducting. Let us continue. So here, if we have a spherical symmetry, we have, let us see the first case, conducting sphere. So this sphere is conducting. What we said, if we have a conductor, there is no charge inside. So if we have a thin uniformly charged spherical shell with total charge Q in cross section, we can define two Gaussian surfaces inside the sphere and outside the sphere. In this case, let us apply Gauss law. So for to surface S2, we have R greater than capital R. In this case, we will have, you can see in the figure that if we are at S2, the enclosed charge is directly the total charge Q. Okay? So when we replace in our formula, EA is the enclosed charge over epsilon 0. So it is E4 pi R square Q over epsilon 0. There is a mistake here, it's epsilon 0. Okay. So E is 1 over 4 pi epsilon 0 Q over R square. This is if we are outside. If we are inside, you remember that if we have a conducting sphere, there is no charge inside. So the enclosed charge is 0, and directly we will write EA or E4 pi R square is 0, and we have E equal to 0. Okay? Now if we have a non-conducting sphere, a non-conducting sphere means that you have a charge in the whole sphere, in the whole sphere. So here, you remark that in the whole sphere, just a minute. Let us continue. So, if we have a non-conducting sphere, it means that there is charge distributed over the whole volume of the sphere. So inside, over the surface, everywhere. Okay, so let us study if we are outside. First, let us study if we are inside. So for surface S1, if R is less than capital R, so this is S1, the enclosed charge is just this part. We can apply Gauss law like this. So phi is EA is E times 4 pi R squared, Q enclosed. In this case, we have a volumic distribution, a constant volumic distribution law. We multiply it by the volume of sphere S1, which is 4 pi over 3 small r cube over epsilon 0. Then we deduce the formula of E in the inner surface. E is rho r over 3 epsilon 0. Okay, so then for r is greater than capital R, so if we are really outside, we will see the total charge Q, so we don't need to work with the rho. I will write directly Q enclosed is Q. So it is E is Q over 4 pi epsilon 0 R squared. And I can replace with a rho, but in this case I have the total volume of our sphere, which is 4 pi over 3 capital R cube. Okay, so in this case, no image. Now now you can see the image normally. You can see the image, yes. Let us continue. So you remark that if we are outside the sphere, we will see the total charge. So I will have the same formula than previously. You will see the total charge Q, and I replace it here. So you can answer here, it's Q over 4 pi R squared epsilon 0, or you replace your Q with the total charge, which is rho 4 pi over 3 capital R of your sphere Q. Okay, and we get the final symmetry. That is, now I know that the internet is very worse. We do our best. Okay, so we have finished this chapter. I'm waiting for your questions. Just write your questions. Did you start recitation or no? For physics, did you start your recitation? With which teacher? Normally you are going to start. Who started? Which one has started? Which teacher? You started with Miss Haddad. Good. And with Mr. Shergi. Mr. Shergi, you started with him? Not yet. And Mr. Shala? No. I'm going to discuss with them. They have to start very quickly. Okay, if you have any question, what you didn't understand, just ask me. Now, let us take time for questions. Yes, I know we did it, but just to let you remember, because it will be included in the exam, and that to be sure that you understood all the main points. Okay, so if you have understood everything and you solved the exercises, next time, inshallah, I will planify the next session to pass to the next chapter. Chapter 1, no, it's chapter 3. It's the third chapter. We review the chapter 3, Gauss law, then we will continue the remaining. Okay, so recitation you have done just chapter 1. Huh? You will solve just some, for recitation, you will solve detailed exercises, just some samples for each recitation. Try to solve and ask questions to the recitation teacher to answer you. Okay, so you must also you must practice the chapters which will be included. Chapter 1, 2, 3, 4. I think we are going to stop to 4. So next session we will see 4, and we will solve exercises for 3 and 4. Okay. Yes, for chapter 4 I will go slowly, but I think it's logical to read because everything is written. I'm going to read, but ask me your question and I can go slowly to explain things. Maybe also I will write things and show them to you. Okay? Yes, we will continue the other chapters till they will tell us at which moment we are going to pass the exams. Maybe we will return back to the university to pass the exams. Normally 6 chapters. I didn't finish the last one in the platform model. Okay, I can insert it also. That is, so if you don't have question, we can finish here. I don't know. I don't have idea how we can go to pass the exam. Maybe peut-être ça va être du présentiel, so you must displace to the university to pass the exam. I'm not sure about that, about this. So let us wait and see. Just study, focus on your study now, and we will see what will happen later. The most important thing is to finish this semester. We try to finish, but with understanding things. Okay, so try to understand and to ask questions, because this course is the basis of many courses of the second year. Okay, so it's very important to understand the main concepts and the notions of the course. Okay, so review your lectures, and I will schedule soon the next session. We will pass to chapter 4. Okay, thank you for attending this course, and see you soon. Goodbye.